Welcome to Metrology lecture series. In the present video, we will discuss the limits and tolerances. In any manufacturing process, it is impossible to make all products exactly the same because production always involves the following three main factors, that is men, machines and the materials. Men make small mistakes which influence on the final dimensions of the part, and machines which may not always perform perfectly, and materials which may not always have the uniform quality. So these factors impact the make the all products exactly the same dimensions. Even when everything is working properly, small natural variations will always occur. If these variations are kept within acceptable limits, we say the process is under control. So in the under control process, we can produce the products not exactly same, but small variations which are in the acceptable limit. In engineering, most products are made up of many parts that must be fit together. So let's consider example, an engine, bicycle or even a ballpoint pen. Each part must be made within certain limits of size so that it will fit properly with its matching part. Let's see the example. Think about a pen and its cap. If the cap is too tight, it will be hard to close. Similarly, if the cap is too loose, it will fall off easily. So to make sure every pen and cap fit well, so manufacturer control the sizes within the specific limits. So manufacturers not exactly produce the same dimensions, but close enough to work together perfectly. Similarly, in machines, parts like the shaft and holes or piston and cylinders must fit together within limit to ensure smooth operation and the long life. Okay, let's see the limits. Limits are the ranges of permissible difference in dimension, which means limits shows the highest and lowest values of the dimensions of a part. Limits are the boundaries of maximum and minimum acceptable dimensions. So we can be say that limits are acceptable range of the manufactured component. The limits of a dimensions of a part are two extreme permissible sizes between which the actual size of the dimension may lies. For example, we have to make a shaft with a diameter of 25 mm. So here actual dimension is the 25 mm, but we are giving the acceptable limit. Let's say maximum limit is the 25.5 mm and the minimum limit is the 24.5 mm. So here 25.5 and 24.5 are the two extreme permissible sizes, and these two limits are lies between the actual size of the dimension, that is the 25 mm. Limits are fixed with the reference to the basic size of that dimensions. So here 25 is the actual dimensions and we are considering this is the reference point. The highest upper limit for the dimension is the largest size permitted and the low limit is the smallest size permitted for that dimensions. So in this example 25 mm is the actual size and permittable ranges we are giving as the maximum limit we are giving as the 25.5 and minimum limit we are giving as the 24.5. Next we will discuss the tolerance. The permissible variation in size or dimension is called as the tolerance. So limits are the boundaries of the size. Tolerance is the difference between these boundaries, which means tolerance is the difference between the maximum limit and minimum limit. The word tolerance indicates that a worker is not expected to produce the part to the exact size, but a definite small size error is permitted. So the difference between the upper limit and the lower limit of a dimension represents the margin for variation in workmanship and is called as a tolerance zone. So let's see in the diagram. So here shaft is having the upper limit as well as the lower limit. So tolerance means the difference between the upper limit and the lower limit. So this zone we are calling as the tolerance zone. So worker can produce the dimensions of a shaft within these ranges. So this zone we are calling as the tolerance zone. So let's consider one example. A shaft of 25 mm basic size may be written as 25 plus or minus 0.02. So this means the maximum permissible size is plus 0.02, which means 25.02. So upper limit of the size is the 25.02 and minimum permissible size is the 25 minus 0.02. So it is the 24.98, that is we are calling as the lower limit. So here upper limit of the shaft is 25.02, lower limit of the shaft is 24.98 and tolerance is the difference between the upper limit and lower limit. So upper limit minus lower limit. So it is the 25.02 minus 24.98, which is the 0.04 mm. So tolerance is the 0.04 mm. So next we have to discuss about the systems of writing tolerances. So there are the two systems writing tolerances. First one is the unilateral tolerances system. Second one is the bilateral tolerance system. First I have to look for the unilateral tolerance system. In this system, dimensions of a part is allowed to vary only on one side of the basic size. So tolerance lies wholly on one side of the basic size, either above or below it. So unilateral system means, so dimensions of the part is varying above or below. Only one side it will be vary. So let's see the example here. Let's consider the basic size is the 25 mm. If you consider the maximum size is the 25.02 and minimum size is the 25.01. So here dimensions of the part is varying only above the basic size. Similarly, we have to look for the another example also. Let's consider maximum size of the part is 25 plus 0.02 and minimum size is the exactly 25. So here also dimensions of the part are varying above the basic size. Let's look for the another example. So let's take the dimensions of the part. Upper limit is the 25 mm and the lower limit is the 25 minus 0.02, it is the 24.98. So here, so dimensions of the part are varying below the basic size. Similarly, another example also, maximum size is the, so 25 minus 0.01, which is the 24.99, and the minimum size is the 24.98. So here, so dimensions of the part is varying below the basic size. So in these systems, the dimensions of the part is allowed to vary only on one side of the basic size. It may be above the basic size or maybe the below the basic size. So the tolerance zone should be the vary only on the one side of the basic size. It may be above or may be the below. Is called as the unilateral tolerance system. Let's see the bilateral tolerance system. In this system, dimensions of the part is allowed to vary on both the sides of the basic size. The limits of tolerance lies on either side of the basic size, but may not be necessarily equally disposed above it. So let's see this schematically. Here, so the tolerance zone is varying above the basic size and also below the basic size. Sometimes it is the equally varying this tolerance zone, but sometimes it may not be equally varied this tolerance zone. If the tolerance zone is equally varying with respect to the basic size, we are calling as the equal bilateral tolerance system. If the tolerance zone is not equally varying with respect to the basic size, we are calling as the unequal bilateral tolerance system. In general, unilateral system is preferred in interchangeable manufacturing, especially when precision fits are required, because unilateral system is easy and simpler to determine the deviations. And another advantage of this unilateral system is go gauge ends can be standardized. Moreover, this form of tolerance greatly assists the operator when machining of the mating parts. Bilateral system, it is not possible to retain the same fit when tolerance is varied and the basic size of one or both the mating parts is to be varied. And moreover, bilateral system is used in mass production where machine setting is done for the basic size. So next we have to look for the relationship between the tolerance and the machining cost. The relationship between the tolerance and the cost of production is as shown in the figure. So here observe that one, the for closed tolerance zone having the higher machining cost and higher tolerance zone having the lower machining cost. If the tolerances are made closer and closer, the cost of production goes on increasing, because to manufacture the component with closer tolerances, for this one we have to need the precision machines, tools and the materials, trained and highly skilled operators, tight inspection and more precise testing and inspection devices. It needs the more concentration of the operators, frequent checking and more time, which slows down the rate of the production, and moreover close supervision and control is essential. So due to these factors, if we are reducing the tolerance zone, it means we have to produce the high accuracy components. So it will be influence on the increasing the machining cost. Next we will discuss the tolerance accumulation. If a part comprises of several steps, each step having some tolerance over its length, then overall tolerance on complete length will be sum of the tolerances on individual length. In this picture, component is made of 3 individual steps and each step having the individual length and tolerances. Let first step length is L1 and its tolerance is L1 plus A minus B. And the second step length is the L2 and its tolerance is L2 plus C minus D. And third step length is L3 and its tolerance is L3 plus E minus F. And let's consider overall length of the component is L and its tolerances is plus G and plus H. Now G equal to the A plus C plus E and H equal to the B plus D plus F. Let's see the one example problem for this tolerance accumulation. The overall length of the assembly is the sum of the individual length of the components and it is given as the L equal to LA plus LB plus LC. So here L is the overall length of the component and LA is the individual length of the components. So L is the overall length of the component L equal to LA plus LB plus LC. Moreover, it is given the length of the individual length, that is the LA is the 30 and LB is the 20 and LC is the 10. Then basic size of the overall length, which is equal to L equal to 30 plus 20 plus 10, which is equal to the 60 mm. So the basic size of the overall length is the 60 mm. Moreover, it is given in the data tolerance zone for the each individual length. So that is the for the first individual length, it is given the tolerance zone is 30 plus 0.02 minus 0.01. Similarly, for the second component tolerance zone is 20 plus 0.02 minus 0.01, and for the third component tolerance zone is the 10 plus 0.02 minus 0.01. So now we have to determine the tolerance zone for the overall length of the component, and we know that when the tolerance zone for the overall length component is the, let's consider, its tolerance zone is the plus G and the plus H. So G will become the, previously we discussed, A plus C plus E, and which is the B, H equal to the B plus D plus F, which means cumulative upper tolerance will become the, upper tolerances for the individual length, that is the 0.02 plus 0.02 plus 0.02, which will become the 0.06 mm. Similarly, lower cumulative, cumulative lower limit is the minus 0.01 plus minus of 0.01 plus minus of 0.01, which is the minus 0.01 minus 0.01 minus 0.01, which is the 0.03. So which will become the 60. So here G value is the plus 0.06 and H value will become the minus 0.03. So answer is the, therefore dimension of the assembled length equal to the 60. So tolerance zone is the plus 0.06 and minus 0.03. Next we will look for the another example problem which is given in ISRO VSSC Technical Assistant for Mechanical in the July 2023. Let's see the problem. In the following figure, what will be the tolerance for the dimension X? So observe the here. So in the figure it is given the overall length, and overall length is given the 200, and its tolerance zone is the plus 0.1 and minus 0.2. Let's consider overall length, let's consider the capital A, and this the overall length is consisting of the 3 individual step length. So let's consider the first individual length, let's consider the B, and its length is given 78, and the tolerance zone is the plus 0.1 and plus 0.2. And the second component we have to determine its dimension, and moreover its tolerance zone we have to determine. Let's consider third component, let's consider the capital C. So its length is given the 52, and the tolerance zone is the plus 0.1 minus 0.1. Okay, let's see the solution. So first we have to determine the nominal length of the X part, which is equal to the X equal to the overall length minus remaining 2 individual length, that is the X equal to 200 minus 78 minus 52. So which is equal to the 70. So 70 is the nominal size. So now we have to calculate in the worst case limits, because X equal to A minus B minus C. So here A is the overall length, B and C is the individual step length. And in the data it is given the overall length having the maximum limit is 200 plus 0.1. So maximum limit will the A max equal to the 200 plus 0.1, it is the 200.1. And minimum limit is the 200 minus 0.2. So A minimum will become the 200 minus 0.2, it is the 199.8. Similarly for the second part, it is given the limits is the plus 0.1 plus 0.2. So maximum will become the 78 plus 0.2. So B max equal to the 78.2. Minimum is the 78 plus 0.1. B minimum will become the 78.1. Similarly, you have to look for the C part. For the C part, it is given the tolerance zones are the plus 0.1 minus 0.1. So maximum limit is the plus 0.1. So maximum limit will become the 52 plus 0.1. It is the 52.1. And minimum limit is the minus 0.1, which will become the C minimum equal to 52 minus 0.1, which is equal to the 51.9. So now we have to determine the maximum size for the X part. Let's consider maximum X, that is the largest possible, which is equal to, when it is the largest value is possible, A max minus B minimum minus C minimum, then only we will get the maximum dimensions. So X max will become the A max minus B minimum minus C minimum. A max is the 200.1, B minimum is the 78.1, C minimum is the 51.9. So substitute these values, we will get the maximum value for the part X is the 70.1. Similarly, we determine the minimum size of the part X. When minimum size is possible, A minimum minus B max minus C max. So here A minimum is the 199.8 minus B max is the 78.2, C max is the 52.1. Substitute these values, we will get the minimum X is the 69.5. So upper limit of the part X is the 70.1 and the lower limit of the part X is the 69.5. So this can be rewritten as the 70 plus 0.1 and 70 minus 0.5. So then the tolerance zone will become for the dimension X is the 70 plus 1 and minus 0.5. So option A is the correct. Similarly, you have to look for the another example problem which is given in the GATE 2007 for the production engineers. So example problem is the tolerance on the dimension X in the two component assemble as shown in the below figure. So here it is given the overall length. Moreover, remaining two parts individual length is given. So then X will become nominal size of the X will become the 50 overall length minus first part and the second part. 50 minus 10 minus 38 which is equal to the 2. So next we have to determine the maximum X. When it is the maximum X is possible? Maximum overall length minus minimum size of the first length and the second length. So minimum length of the first part is the 9.99 and the minimum length of the second part is the 37.985. So maximum X equal to the 2.045. Similarly, we determine the minimum X. So when it is the minimum size is possible? So minimum size of the overall length minus maximum size of the remaining two individual length. That is the minimum size is the 50 minus 0.02 which is equal to the 49.98 and maximum size of the first component length is the 10.01 minus maximum length of the second component length, that is the 38.015. So this minimum X will become the 1.955 mm. So maximum X equal to 2.045 and minimum X is the 1.955. This can be written as 2 minus 0.045. So then the tolerance on the dimension X will become the 2 plus or minus 0.045. So option D is the correct. So next we have to discuss about the compound tolerance. When tolerance is determined by established tolerance on more than one dimension, it is known as the compound tolerance. For example, tolerance for the dimension R is determined by the combined effect of tolerance on 40 mm dimension on 60 degrees and on the 20 mm dimensions. Then tolerance obtained for dimension R is known as the compound tolerance. So how we will get the R value here? So 40 minus 20 divided by tan theta. So R max, maximum when it is possible. So 40 max minus of 20 minimum divided by tan theta max. Similarly, when the minimum value is possible, so 40 minimum minus of 20 max divided by tan theta minimum. So this is we are calling as the compound tolerances. So tolerance we are obtaining for the dimension R, we are calling as the compound tolerances. So this is the limits and tolerances, and thank you.